The meeting of two personalities is like the contact of two chemical substances. If there is any reaction, both are transformed.
The Interplanetary Podcast. The exploration of space for the benefit of all humankind. Your hosts in England and Sweden, Matthew Russell and Linn Boldt-Christmas.
Oh yeah, baby. Carl Jung. Jung.
I mean, the Swedish me, I want to say Jung, I guess. Jung, I don't know.
I think it is Jung.
The famous psychiatrist guy.
Yeah, I think you got it right. I'm pretty certain. Yeah. How are you, Linn?
I'm good. How are you?
I'm good. I'm going to open this with an apology about how long this episode has taken to come out. Been busy with lots of life. I managed to get COVID.
Oh no!
Which wasn't too bad. I'm vaccinated up, so make sure you get vaccinated up.
Triple dose, everyone.
I was triple dosed, and then I've managed to avoid it. I don't know how I've managed to avoid it, but I eventually succumb. So that was that. And then, unfortunately, my dad died. And I'm going to dedicate this episode to my old man, Richard Russell.
You should.
His claim to fame for space thing is that he came from Kent, which is where he went to school with James Burke. Have you ever seen that clip where James Burke is walking and he's explaining rocketry? And von Braun, and then he points to a rocket just as it ignites and takes off. It's a very famous clip.
It's amazing.
So my dad went to school with him.
Really?
So, that's his little and also he used to hear and see the V2 rockets going over Kent when he lived there as a child during the Second World War. Yeah. And as when he was doing his national service, he actually sort of went to the places in Germany where the rockets were actually built. He actually went to sort of one of the V2 that were sort of hidden underneath these massive. It sounds like a Thomas Pynchon book. yeah, it does a little bit. So my and my dad got me into music. So I'm dedicating this podcast to my dear old dad who passed away a couple of weeks ago.
Absolutely, to him.
The other news is that Linn and I are going to go monthly podcasts. Isn't that right, Linn?
Yes, it is.
Yes,
and I'm very excited to become a more permanent fixture of everybody's ear holes.
Yes.
I'm so sorry. the Patreon subscription will now plummet like a V2 rocket.
So it's going to be a monthly podcast, which obviously we're going to up our podcasting game.
Yes.
So it may return weekly one day when I get less busy in life.
Who knows?
But who knows? But yes, it's monthly, high quality, with the marvellous Linn, very popular co-host.
We're going for quality over quantity in this case.
Yes, exactly. We're starting with now. So tell us a little bit about our guest, Linn.
So today we have a very exciting guest who I guess is kind of like the third installment in a little series. We had our wonderful astrobiology guest and our wonderful astrogeology guest, I guess. And so today we have Dr. Catherine Walsh, who is at the University of Leeds, who's a very, very wonderful person. I happen to know Catherine because I did my master's at Leeds, and she was very inspirational and very kind. She's a very, very excellent, both an excellent scientist and an excellent person. And I absolutely demanded to have her on the show because she has the coolest job. I feel like in space, everybody has kind of a cool job because it's space related. But astrochemistry, is this not just the most wonderful combination of words in the entire world? Astrochemistry.
It's very cool, as you'll hear. It seems to be a very important area of study, right?
Absolutely. I mean, and you know me, I always bang on about my dear exoplanets, but absolutely in any kind of planet formation, really it's chemistry. And all the other parts about how planets form, the formation processes are, you guessed it, rooted in chemistry. Because all these fun things like pressures and temperatures and stuff like that, it is really in the chemistry domain. Blurred lines to physics, fine, but if we're looking at how do atoms and molecules do stuff, then I would argue this is more chemistry than physics.
Yeah, and I really love that whole concept of even the physics, even the sort of big physics, the kind of stuff that you'd think, why is that happening? is affected by the chemistry and
absolutely.
Because
and vice versa.
It's very, very counterintuitive, isn't it? Because space is different to our experience here on Earth.
100%. This is something that Catherine will very much underline. I mean, when you think about chemistry and you're picturing like little cute purple test tubes and pouring liquids into one or the other, space is a whole different game. It's we've got magnetic fields, we've got low temperatures, we've got high temperatures, we've got everything you can imagine and more. It's terrifying.
Indeed, it is. Well, it's so terrifying. It's really long interview, so I think we should probably get straight to it. What do you think?
Let's do it.
Ekute!
The Interplanetary podcast, putting the ace back into space.
So we're joined on the podcast by Catherine Walsh up at Leeds University. Welcome to the podcast, Catherine.
Thank you. I'm very happy to be here.
So you're an astrochemist. Take us back to roughly what that's about and how you got into it.
So astrochemistry is effectively the study of chemistry that happens in space. So, you can think of typical chemistry being done in a lab where you have someone maybe mixing some liquids or working with some gas in a laboratory and making measurements. But we do exactly the same thing, except that we're looking at chemistry happening in really, really extreme environments. So on Earth, we are about 300 Kelvin temperature. We have a pressure of about 1 bar. But in space, you've got a huge range of different conditions under which chemistry can happen, from very, very tenuous, where you've only got a few particles per centimetre cubed, all the way up to dense atmospheres like the Earth. And Venus, for example, would be another example of that. And you're going over many, many orders of magnitude temperature range as well, from very, very cold environments that are only a few degrees above absolute zero, all the way to thousands and thousands of Kelvin, which would be like in around a star, that kind of thing. So the chemistry that happens on Earth happens over a very small parameter range, but the chemistry that happens in space happens over a huge range of physical conditions, not only just in temperature and pressure or density, but also the fact that if you're nearby a very hot star, then you get radiation happening that kind of triggers a lot of very interesting chemistry as well. So what do astrochemists do? Well, we study the chemistry that happens in those extreme environments, and we're really interested to see how molecules form and are destroyed over that huge range in physical conditions. And that's just very interesting from a physical chemistry perspective, because it's taking us outside of what we know on Earth. The other side of it is that molecules, which is really what we study, it's molecules rather than atoms. Molecules have a huge amount of information about their environment. So we can actually see light coming from molecules, usually at very low frequencies, much lower frequencies than our eyes can see. And that light tells us a lot of information about the molecule itself, how abundant it is, how warm it is, but also tells us something about the environment too, such as what the density is, what the UV field is, the radiation field is. So there's kind of two sides of the coin. There's number one, looking at physical chemistry in extreme environments, and number two, using light from molecules in order to learn something about the environments that they're sitting in. So as an astronomer, that's all you have really is light. You can't, you have gravitational waves now as well, but anyway. We're in the era of multi-messenger astrophysics, but most astronomers use light to kind of figure out information from their environment.
And I'm assuming that gravitational waves are of no use to the astrochemist. Or are they? Or
I'm not sure. I'd have to think about that. I mean, they're definitely a signature of extreme events. You have to have something very extreme happening, like, neutron star mergers and things like that in order to generate gravitational waves. But gravity is such a weak force. It doesn't really talk to the scales that molecules are existing on, which is more, Coulomb force, that kind of thing, electrostatic forces, yeah.
So I mean, obviously the obvious question then is how on earth? Well, there's two questions I thought was like, how on earth do you study the chemistry that's light years away,
yeah.
and how do you because you said there's two sides to the coin. Presumably there's a bit of unraveling there to do as well, if there's light from the star and there's light from the actual molecules themselves, or have I got that kind of wrong?
You can't really just go up to a big gas cloud with a beaker and like scoop it up and be like, oh yes, delicious, here's some gaseous methane or whatever.
Exactly. Yeah. So how are you doing it? Is it presumably it's telescopes?
Yeah.
But are they space or land-based telescopes the most useful?
We use both, actually. And again, molecules are really interesting probes. Other than atoms would be the other thing that people think that shine with light. We all know about, atomic spectroscopy. If you remember from chemistry, you burn potassium and it's purple, I think. Sodium is yellow. Those are electrons jumping around in the jumping around in the atom. That's then creating light at very discrete wavelengths, which tells you what atom it is or what metal it is. And we use the same principle for molecules, except molecules are more powerful than atoms because they emit light right across the entire electromagnetic spectrum, all the way from kind of radio waves up to visible and UV wavelengths, which is where we typically see atoms like hydrogen and helium as well. And the reason for that is because molecules, so they're a collection of atoms that are bounded in a particular way through covalent bonds, which means that they're identified by the fact that they have a unique shape and they're made out of a unique combination of various atoms. So you not only have electrons jumping about in molecules, molecules can also rotate and change energy state. Oh no. Yeah.
It's so much worse.
And they can also vibrate and rotate at the same time as well and change energy state as well. So, and these transitions tend to happen at longer wavelengths than atomic or electronic transitions, which are visible UV wavelengths. And that's really powerful, actually, because you only excite atoms in really hot gas, like in a star. But if you want to see something like Linn says, like a gas cloud at 10 Kelvin, you're not going to get any electronic transitions happening there.
Right.
What you are going to get are small molecules that can change rotational state. And then jumping between those rotational states, they emit light, and they emit light at long wavelengths, typically. So if we take like the most commonly observed molecule in space, that's carbon monoxide. It's a bit boring, but it's useful. I prefer bigger, more exciting molecules. So carbon monoxide rotates. It's a linear rotor.
Sorry, carbon monoxide, if you're listening.
We don't really like it here on Earth either. It's a bit dangerous.
Bit deathy, yeah.
It's got bad press.
Yeah, it's got a bad press on Earth, but it's actually really useful as a molecular probe in space. But it can rotate and change energy state. And when it rotates, it emits light at microwave radio wavelengths, so a few millimeters. And to see millimeter wavelength light, we use radio antenna effectively. So the telescope that I would use most in my research is ALMA, which is Atacama Large Millimeter Submillimeter Array. And it's a huge array of telescopes in the Atacama Desert in Chile that operates just about millimeter wavelengths. And that's what we use kind of to look at, especially at high resolution, to look at objects at high resolution. But carbon monoxide and other simple molecules like water and like CO2 would be another one, also have vibrational transitions. And those are higher energy because it takes more energy to make a molecule vibrate than rotate. I mean, you know that yourself. If you've got, a ball on a string or something, you have to kind of pull on the string or pull on the elastic to make it vibrate. But to actually make it rotate doesn't take very much energy at all. So you can kind of get that principle.
That makes sense.
But the infrared, so vibrational transitions happen in the infrared. And there, especially for molecular vibrational transitions like CO2, water, we really need to go to space for that. Because the Earth is about 300 Kelvin and emits quite strongly in infrared radiation. So we kind of need to get away from the Earth, go up into space, shield ourselves from the sun and everything to cool down sufficiently to see vibrational transitions of molecules. For example, the next big mission that will do that is JWST, which is, I think, in science commissioning at the moment. And
I think so, yeah. Woo!
They've got the...
Can't believe after however many decades.
Yeah, so
this is where we're at.
We now have a brand new infrared mission. And James Webb or JWST, whatever you prefer to call it, it's a big debate over the name, of course, we'll be looking at those vibrational transitions in molecules primarily. So that's kind of those, I would say ALMA and JWST are two big astrochemistry telescope powerhouses at the moment. Yeah. But obviously there's a lot more facilities right across the globe that we use as well. We're not just constrained to big arrays of telescopes. We can use single dish telescopes as well.
And I feel like it's a big question that's either really obvious or not obvious at all, but like, what are we looking for, when we're looking at planet forming disks and stuff like that, or the question that we're looking for the answer to.
So you're talking about disks now around young stars?
I guess in every sense, because something that I thought was really cool when I first learned about it is there are so many molecules in space. And everyone's like, oh, hydrogen this, hydrogen that, it's 98%. Yeah, but there are still so many different kinds of molecules. And not only that they exist in the first place, but that we actually have been able to conclusively say, this is what this molecule is. I think that's so cool. Yeah,
and I think that we've been able to do that because of what we call laboratory astrochemistry. So that's where we try to mimic the conditions in space in the lab. And we try to recreate. So I think, Matt, your question was like, how do we, the two sides of the coin? Well, we've got the light that we see with the telescopes. But on the other hand, we have a huge amount of laboratory and experimental effort going on trying to replicate what we see, or not even replicate, to understand what we see. So effectively making a little interstellar molecular cloud in a lab, if you like, to try to understand why these clouds are composed of the molecules that they are, but also how those molecules have formed and survived in those environments in the first place. I've forgotten your question, though.
Well, I'm going to ask a pre-question to Lynn's, which is what would probably need answering is what are the places where you find astrochemistry? There's no point just pointing into deep space, right?
Absolutely.
Well, even so, everywhere is. But are there special places? We mentioned protoplanetary disks. I would imagine that's quite a good place. But are there other places other than those?
I think we can look at it on different scales. So, for example, let's start on the largest scales, and then we'll come down to planets. So, on the largest scales, we do astrochemistry of galaxies now. So galaxies that are not the Milky Way, other galaxies, right? And I'm not a galactic astronomer or extragalactic astronomer. So my knowledge is really just about what we're kind of learning astrochemically.
Galaxies exist.
Galaxies exist, but they're different.
Let's leave it at that.
They're different from each other.
Yes, to some extent, probably.
But they have a sort of average chemical content or something?
Like kind of so.
I guess that depends on the age.
And starburst, like star formation activity, metallicity, so how many heavy elements you have relative to your lighter elements. So there's people doing now extragalactic astrochemistry. So really looking at what the composition of on a galactic scale is in galaxies that are not the Milky Way. We have a very, very kind of narrow view of the Milky Way because we're inside of it. So, we kind of have inferred the morphology. It's got at least 2 spiral arms. There's probably more satellite arms. We've kind of been able to map that using molecules, by the way, and hydrogen.
Thank you, molecules.
Because they give you...
And hydrogen gets a shout out too.
They tell you how the gas is moving. But actually trying to place what we know about the chemistry and molecular composition of our galaxy in context, people are doing on galactic scales. And they're resolving the chemistry that's happening, very, very close to the galactic center, around, the black hole, or even around kind of very active galaxies. And then looking at how that chemistry varies as you move away from the galactic center. So that's kind of the big scale picture. Now we kind of zoom into our galaxy. The biggest regions that we look at in astrochemistry are star formation regions. So places, big gas clouds, like Linn has said, where either stars will form. These are the cold environments, so they're dense enough for star formation to happen at some point in the future. And why do we look at the chemistry in those environments? It tells us something about the composition of the gas that will form those stars and their surrounding planetary systems.
So that's like stellar nurseries, things like the Eagle Nebula.
Exactly. So you're probably very familiar with the Eagle Nebula kind of optical light image, where you have the kind of pillars of creation, which are dark in that image. And they're dark because they're full of molecular gas and dust that's kind of obscuring the light that's being emitted by the kind of cluster of stars.
Yeah, they're not empty.
They're not empty. They look empty in an
the
optical.
Opposite.
They're actually really full of dust and gas. So
you're able to look at the chemistry of those dark clouds and again, we look across many different star formation regions, different ages, different masses, and kind of look at the variation of composition that we see across those different star forming environments. And we also look at environments that are forming high mass stars, like towards the galactic center. That has a very different chemistry, actually. The galactic center is kind of really, really full of very, hot, warm gas that's really efficient at making complex organic molecules. So molecules that are quite large, around 6, 7, 8 or more atoms, and contain carbon. And that environment just seems to be really, really provide a really rich environment for creating these quite large species. So we see a difference in chemistry between nearby star-forming regions that will form low-mass stars like the Sun, but also towards high-mass star-forming regions towards the galactic center, where you'll form probably a population of high-mass and low-mass stars together. So we see chemical variations across those different environments. And then if we kind of zoom in again, and we're looking kind of around an individual star, if you take another area where molecules are really, really important that I don't think people appreciate. I'm becoming like and I teach this to my undergraduate students as well. I don't think they appreciate it. Maybe not for the same reasons, but anyway, they're just a bit bored and want to pass their exam, really. So stars form from the collapse of clouds, basically clouds of dust and gas. And for that to happen, you need gravity to win over thermal pressure. So thermal pressure is pushing outwards and gravity is pulling inwards. Now, in order for a collapse to happen, gravity has to win. So that means you have to reduce the thermal pressure. And the only way you can really reduce the thermal pressure is by cooling the cloud, because that reduces the temperature. And the only way that you can cool the cloud, because it's very low density, is through radiation. And because it's very low temperature to start with, the only radiation you can emit is via molecular rotational transitions. So stars only form because we have molecules that are able to radiate away energy and actually cool the cloud significantly, such that gravity wins over thermal pressure. So how did that work in the very early universe? Is that a bit of a mystery?
Really good question.
About the first stars?
Really good question. There's a huge area of research which is about the first stars. The conditions then were probably much more dense than they are now. So we don't have the same kind of issues with kind of collisions. So collisions would have been much more common. But it's a really good question. And the first stars were probably very massive and, of course, had to be formed from clouds of just hydrogen and helium and a bit of lithium or whatever else we had then. But the first population of stars would have looked very different to what star formation looks like now because of this effect. Yeah.
And I guess also if it was mostly hydrogen, then that also affects what kind of thermal pressures arise in a hydrogen gas versus a more molecular gas.
Exactly. Yeah. So the same physics still.
That's really cool.
Yeah, the same physics would still.
Super cool.
But the same physics would still have had to have applied, but the physical conditions would have been very, very different, which meant that you weren't maybe limited to. You wouldn't have needed the molecules in order to get gravity to win so much in those early times. Yeah.
So then, where did molecules come from? I mean, they elements are formed in the stars and stuff like that. But I mean, the more crazy out there molecules that we start seeing, like you have these longer carbon chains and stuff like that. Where do you think? Do we know where those came from? How they started forming? How long ago? All these stuff.
So I think we've got a fairly good understanding of kind of the basic processes that happen through many, many decades of effort. So astrochemistry would have started back in the 1950s when the first...
Oh, that's recent.
Yeah, when the first molecules were detected in space. And it's kind of just accelerated since then, of course. So I think you mentioned the first important step which is that you have a generation of stars that burn lighter elements and create heavy ones, and then they, through their kind of stellar death processes, which can be supernova or supernova or AGN winds, sorry, not AGN winds, AGB stars, asymptotic jam branch stars have outflows that kind of continuously pump dust and gas into the interstellar medium. So that's the first important step, because you need your heavy elements in order to make molecules that aren't hydrogen, H2.
Yeah.
And the next thing that you need, so if you imagine that you've had that first generation of stars, you've got your interstellar medium, which is the space in between the stars. So in order for a reaction to happen in that kind of environment, you need two things to meet. And when these two things meet, you kind of need the reaction to happen straight away. You can't have any activation barrier or anything like that, because you're just at such low temperatures, you just would not have enough energy to overcome that barrier. So a lot of chemistry that happens in the interstellar medium is ion molecule chemistry. And that's where you have an ion, so a charged molecule or atom that reacts with a neutral molecule or atom, because it can happen both ways.
Yeah.
And that interaction is actually an attractive interaction, because you've got a positively charged molecule that is approaching a neutral molecule, but that has an electron cloud that actually polarizes that molecule, creates a little slightly negative charge on one side, slightly positive charge on the other side. And that actually helps to enhance the collision of those two species. And
like two magnets going across a table.
Kind of, it's a Coulomb-like interaction with Van der Waals kind of. There's a polarization that happens that creates an electrostatic enhancement, if you like, of the two reactants. So, and a lot of the molecules that we see in space happen through these pathways. So basically two things collide and they react upon meeting immediately. And actually the reaction rate can even be enhanced because one of them has an electric charge. And there was a huge amount of work done, I think, back in the 1980s, I think, just looking at these ion molecule reactions. So we actually have a really good understanding of which reactions happen. Laboratory astrophysics has provided a huge amount of data that we need to interpret our observations, like reaction rate coefficients, which tell you how fast a reaction happens. So we have a pretty good understanding of that. We think that that's very much how some of these very long chain hydrocarbons actually form. And they form through these subsequent ion molecule reactions where you kind of insert a carbon each time. And then maybe the energy is carried away by a hydrogen or something lighter like that. But there's kind of other chemistry that happens as well that has been less well studied and is only really coming into the fore now in since maybe the 1990s onwards, and that's surface chemistry. So things actually sticking to a surface and reacting on the surface. And for example, water's everywhere in space. Water's not a particularly scarce molecule. It's really important for life. We know that, but it's not particularly hard to find in space because it uses oxygen and hydrogen, which are the most abundant elements that we have in space. But the way that most water forms in space is actually on the surface of dust grains. And the way that it forms is that you've oxygen atoms stick to the dust grain, and then hydrogens can add. And this doesn't need any energy. It can all happen at 10 Kelvin. So you can form
which
water,
is very cold.
which is, it's almost the coldest you can really get.
So the water is ice when it's formed, right?
I guess it's ice flakes. Little tiny snowballs crystallizing and growing.
Yeah.
It's a Christmas miracle.
It almost seems impossible that you could have a reaction that creates ice in the first place.
Yeah.
It's mad, isn't it?
Yeah. So the conditions are such that, and this is why it's really hard for us to recreate in the lab. It's low density and very low temperature. So you don't have a liquid phase of matter. You've only got gas and ice. and then the exchange between the two, which is adsorption and sublimation, effectively. There's no liquid phase because we don't have the pressure needed to create or help something like water stay. You really need to be on a planet for that to happen.
Well, I mean, it's even hard on Mars, isn't it, to keep that without things sublimating and having a liquid
exactly,
phase,
because I think Mars is a couple of orders. Is it 1 millibar on Mars? I think at the surface, something like that. And that even is too low pressure to kind of maintain a liquid water presence on the surface. Yeah.
Which doesn't make it very ideal for life on Mars.
I think this is
not great.
I'm not running there to live there. That's what it is.
I don't really get the appeal myself. It's a fascinating place, but I mean, the terraforming would have to have been very advanced by the time I would map myself to a rocket.
I'll take my chances with Venus.
We need to go the other way with Venus, wouldn't we? We need to kind of lose heavy elements in Venus's atmosphere and make it lighter. Yeah.
No, exactly. I'm assuming when you were telling us your story of zooming out from galaxies all the way down to, you kind of leave it at planets. Would that be exochemistry, or do you delve in that? So
I think like by the time we formed our star, molecules have been very important in that process, as I've described. So we create, planets form within what we call these protoplanetary disks around young stars, and they form really naturally through the physics of collapse with rotation. It's basically just, material moving inwards. It's got some viscosity that's spinning, like a pizza base. It's got some pliability. You spin it, it flattens out. It's kind of a similar principle. So you're kind of exploring the use of the centrifugal force there as well to keep things confined to what we call the ecliptic plane of the midplane of the disk. And these disks are typically much more dense than the interstellar medium. So we kind of get almost a different phase of chemistry that starts to happen at that point. We have, for example, I think, Matt, you'd mentioned, the concept of ice in space, and, I followed that up with saying that we've only got two phases of matter. So there's a really important region in disks around young stars, which is called the snow line. And this happens in the midplane of this disk that's orbiting around a young star. And because as you move away from the star, it's the star itself that's controlling the temperature of the disk. So as you move away, the temperature decreases. Remember, these are much denser objects as well than the interstellar clouds. And you'll reach a temperature below which water can't exist in the gas phase anymore, and you create water ice again. Or the water ice you've inherited from an earlier phase kind of sits in that region of the disk. So inside the snow line, you've got water gas. Outside the snow line, you've got water ice. And you have actually multiple snow lines as well. So CO2 would freeze out or adsorb at a lower temperature than water, so that sits further out. And we even get regions in disks, because they're so dense, where we even lose carbon monoxide from the gas as well. And that's all frozen out. Monoxide? Yeah, so basically in the outer regions of disks, there can only be hydrogen and helium. Because you've actually... Really? Yeah. Maybe tiny amounts of other heavier molecules. Trace. Yeah, so you kind of end up with this kind of, radial stratification of gas and ice abundances just because of the different sublimation properties of the different molecules. Yeah. Couple that with the fact that you're being irradiated by a star, a very close by
a young star, so maybe a very angry UV kind of,
and then you end up
pubescent tantrum star.
Yeah, especially when it's young, it can kind of, have a few tantrums and blast out a lot of X-rays.
Exactly.
Accelerated particles.
It's not a phase.
Teenage phase, yeah.
Exactly.
And all that radiation penetrates the kind of top of the disk and kind of creates also a vertically stratified chemistry going on. So you've got all this ice stratification going on in the midplane, and then through the disk atmosphere, if you like, you've got another kind of vertical stratification going on. Yeah.
The pizza dough has like a cheese-filled crust. There's like some stuff going on in the middle.
Or you've got multiple layers in your pizza. So you've asked the pizza.
It's more like a lasagna at that point.
Yeah, a lasagna would be better.
It's like a lasagna
I'm hungry now.
Or actually more like a pizza made from phyllo pastry or something like that.
Yes,
It's
exactly.
Yeah.
Okay, now I'm definitely hungry.
No, I'm going too far. We stretched the analogy.
But the only difference is in your lasagna pizza, the upper layers are hotter than the inner layers. Because usually when you dig into your lasagna, it's like lava at the bottom. It's the other way around.
Exactly. Okay, opposite way.
So all this chemistry that happens at this phase is essentially then what sets what happens with the planets that form there.
Yeah.
So
yeah, I can imagine. I mean, the planet formation processes we've talked about on this podcast before, and like it's so complicated, and frankly, we don't know exactly. And there are the thing I always talk about that I love about planets. I mean, stars in all their glory, but they're more predictable in a way. You can kind of say if you know X, Y, and Z, you can kind of say something about its age and its mass and all this stuff. But planets are wild. You can't be like, oh, this one is this mass, so therefore we know this thing. Like they're much less consistent, let's say. And I guess it all comes down to the chemistry from the disk.
And I think we're starting to understand a little bit more about that. And again, this is even newer science because this is the exoplanet.
Yeah.
Basically, we see the solar system and we have some, the snow line that I mentioned is quite important because we think the snow line set where the terrestrial planets formed, which are ice poor in the inner region, and where the gas giants formed, which are not so much ice rich, but at least heavy element rich, which would have been through the accretion of these ices. And we've had that picture for a few decades now. But now that we're kind of getting into the era of proper statistics on exoplanets, although we're still biased by what we can see, which is we still can't really see a Jupiter very well around a sun-like star. We can't detect an Earth yet.
Yeah.
So we're still kind of a triangle of our parameter space we haven't populated. But there's so many strange things we see that I don't think our traditional picture of how the solar system formed fits at all.
Yeah.
And I think part of the answer to that query or question is that all these disks look very different from each other.
Yeah.
And there's a huge diversity. And whilst they might share some characteristics, the sheer diversity that you can have through just your mass distribution, your heating from your star, the chemistry that happens, just leaves some kind of fingerprint on the type of planetary system you form then.
Absolutely. It's like the soil from which the flowers grow. And then on top of that, you've got all the different kinds of weather and all the different kinds of seeds.
Yeah, that's a nice way to think about it. Yeah.
Yeah.
I mean, it's even worse than the soil gets affected by the plant that's growing in it.
Exactly.
As well.
And what part of the world is it? And like,
exactly.
Is there an angry teenage sun nearby? All this stuff.
How complicated do the molecules get? I mean, I've heard, obviously you see those news articles where you can get drunk in
the ethanol.
They're all made of methanol and things like that. But I mean, how complicated does it actually? How big can these organic chemicals get or carbon chains get?
And as an addendum to that, when we're talking organic, we're not talking life necessarily, right? Because people hear organic, then they think like organic chicken, free range molecules.
Yeah, we're just talking about having some carbon.
Yeah.
Okay.
Which life does need, because it's kind of the backbone of many.
Carbon-based part.
We're really just big bags of molecules at the end of the day.
Delicious.
Yeah, delicious.
Yeah.
So how complex can they get? It depends on the environment. So the biggest molecules we've seen in space are very weird. They are the Buckminster fullerenes, and they look like a football. And they're carbon. Yeah, the carbon-60.
The buckyballs.
Yeah. And there's no hydrogen. They're just a buckyball. And they're really weird. How did that form? I don't know. That is such a stable. How did you go from carbon atoms to something that is very regular and stable?
Yeah.
That's really interesting.
Well structured, yeah.
Very well structured. And we see buckyballs in actually quite chemically interesting regions, which are in planetary nebula. So this is the phase after, it's kind of the phase after a star starts to throw out its outer layers and is evolving into usually quite a complex, beautiful planetary nebula. So you've maybe seen quite a few nice, beautiful, visible wavelength.
It's like the Eskimo Nebula and the Iris Nebula. All those beautiful
the
ones,
wallpapers.
Yeah, the ones we all have as wallpapers on our
exactly.
laptops, yeah. And the Buckminster fullerene was detected in one of those. So there's obviously something about the physical conditions after these stars die that really allows formation of these large, stable molecules. And then kind of on the other end of it, which is kind of where your carbon chains can go. So we're kind of getting up to 13, 14 atoms, I think.
Wow.
They're the biggest ones that we've seen. Yeah, so you've got, I think 13 atoms is the longest carbon chain we've found. And that's a really weird molecule. That's 11 carbon atoms in a straight line with a hydrogen at one end and a nitrogen at the other end. Very weird. Why? There's loads of hydrogen.
The listeners did not just see the wonderful shrug that Catherine just did.
And I hinted that we think we know how these long chain hydrocarbons form. It's ion molecule chemistry where carbon gets inserted sequentially. But it's still a really weird molecule. You'd never form that on Earth. Yeah. Right? But we see it in interstellar clouds. And
amazing.
Then we can kind of see what we would call complex organic molecules. So I think you'd mentioned ethanol. We can see things like acetone, if you remember from your organic chemistry in school.
Oh, yes.
I suppressed it. Ethers.
I was going to say, what's the one that smells like pear drops?
Is that the ester?
That's the esters.
That's esters and ketones.
What's the most life relevant? I feel like this is I sound like a journalist who's shoehorning a pop science headline into this. But what's the most life relevant molecule that we found?
You'll see. There's been a raft of papers recently which are finding more and more complex molecules that are kind of precursors to bits of amino acids or bits of sugars or bits of fatty acids. So those kind of key molecules that life needs, which are amino acids, proteins, fatty acids, things like that. We don't see them, at least not in space.
No.
But we see things that kind of look like they could be part of the reaction chain towards these larger molecules.
Yeah, but just because you find them in planetary disks, these kind of complex, building blocks for amino acids, doesn't mean that they survive planetary formation.
This is the thing. So, the water that we find in protoplanetary disks, if we do, would water have been on Earth surfaces from the beginning, or would it have been added later on? Do you know what I mean?
So there's a few different questions there. So I want to clarify, we don't see these big molecules in disks, unfortunately, because they're really tiny objects, but we see them more in star-forming environments.
Okay.
We're still a bit limited in what we can see in disks. But your question on whether or not molecules can survive star formation and the assembly of the disk, I think that they can. And this is another facet of astrochemistry that's quite interesting that I haven't touched upon, and that's something called isotopic fractionation, fancy term. So at very low temperatures, molecules prefer to have heavy atoms rather than the lighter atoms. So what you end up getting at low temperatures is, for example, something like water, Linn, like you said, preferring to have deuterium instead of hydrogen. So you make things like heavy water.
Heavy water, yeah.
So HDO or D2O. And that applies to other molecules like formaldehyde would prefer to have HD CO instead of H2CO. So at low temperatures, you get an enhancement of the deuterated version of the molecule versus the regular version of the molecule.
So that's so this ends up being like a fingerprint. I'm assuming.
Yeah. So and we can,
I guess like carbon dating style of the ratios of isotopes.
A little bit. I think what those isotopic ratios tell you is something about the temperature history of that molecule. Because if that molecule had been exposed to higher temperatures at some point in its life and had never seen lower temperatures again, then you would expect that isotopic fingerprint, if you like, to have been erased.
Yeah.
But we see enhancements in disks, and we see enhancements in the solar system. So we do think that a lot of the objects we look at have assembled quite quiescently, and that some of the, ice and stuff that we have in the outer solar system hasn't actually seen high temperatures and has actually just been brought down, and it's been sitting in the disk ready for planets and comets and things like that to form. So there is some evidence that some of the material we have in this, and our best evidence is the solar system, of course, because we can actually touch almost the material in a way. We see,
can nearly go and do the scooping out.
So we do see enhancements. So, like, for example, the water on Earth is heavier in deuterium than the underlying deuterium elemental ratio in the universe. So there's an enhancement there that's been preserved. And we think that that's a pretty good indicator of late delivery of water via impacts from asteroids and comets.
Yes.
So it's not that the water was present when the Earth was there. That would have the isotopic fingerprint of whatever temperature the Earth was forming at. But actually, we have been able to deliver colder material. So this is kind of this is astrochemistry again, giving us information about something about the history and environment.
Thank you, astrochemistry.
Within which, the Earth even formed as well.
I have a really formative childhood memory of this, of like being at some kind of science outreach thing, and I was like 6 or something, and I remember being told, we don't know where the water on Earth came from. And I was like, no way. I need to study this.
There is, you'll still see a bit of debate about it in the literature. There's still some schools of thought that the Earth accreted what they call wet.
Right.
So that there was ice available at the time that the Earth formed, and that what we see now is that ice, a mixture of some late delivery and the water seeping up from the Earth. So I would say it's still not solved, but certainly the evidence kind of points towards.
The analysis of Rosetta.
Yes.
It wasn't particularly helpful, was it? They were expecting it to be more of a slam dunk for cometry delivery, and it turned out not to be.
And I think what Rosetta showed us that was really interesting was that, we have a terrible habit of classifying things in astronomy, and we like things to be in nice boxes, and the school of thought was that the Oort cloud comet sat in this nice box, and the Kuiper belt objects, short period comets sat in this other type of box, and actually that's not the case at all. That these two populations are not so distinct. So again, really interesting from thinking about just the history of all of the material that's been in the solar system for 4.5 billion years.
I suppose that whole thing of misclassification it's a bit like taking clothes out of a washing machine and trying to work out what order they went in when you put them in.
That's a really good analogy. I like that.
But we've spoken about that before. We spoke about the Nice model for how the solar system formed. At the end of the day, we can't go back in time and check. There was no CCTV footage. We can't go back and be like, oh right, this is how that happened. We can extrapolate our best guesses, and we can see evidences, but I mean, really, it's doing CSI on a very old site crime scene.
So the next best thing that we can do is look at and try to measure the composition of the comet forming regions and disks around other stars. That's not giving us insight into our solar system, because we can't do that, but it at least gives us an insight into other forming planetary systems, and we can kind of start to say, right, what do they look like now, because they will evolve into another planetary system. So we can do that test, but it's true that it's just so much has happened over the past few giga years that to try and disentangle it all is really, really hard.
And I mean, that's also the kind of the motivation to look at, well, really anything in the universe. And when we started looking at different solar systems, which was not that long ago, in the grand scheme of things, imagine that you were a human and you had never met another human ever, then you might look at your hands and be like, well, I have 5 fingers on this hand and 5 on the others. Is that too many fingers? Is that not enough fingers? Or if you were born with purple hair, and you might be like, well, obviously everyone has purple hair, but what else is different? So with a sample size of 1, you can't say that much. And
No.
I think this is like looking at these discs that we talked about and stuff like that. The more we look at, the more we can start to see what are the similarities, what are the differences. And the things that they have in common might then be a sign of a grander structure or mechanism on how that works. And then the anomalies can be all the little fun personal quirks of each system.
Yeah, exactly. And I think that's the way that especially for disks around young stars, that's the way the field has to go now. We've been we've been kind of doing that, very detailed studies of individual systems that we know very well, finding out that they're all different from each other and different to what we expected. But we really expand out and really start to do kind of systematic chemical studies of these, of disks around stars and, across a different range of star forming regions. And I'm hoping, with ALMA, that's something that we'll be able to move towards in the future to do that. And
definitely.
really place what we know about the solar system in better context, I think.
Yeah, so what are the priorities of the astrochemistry community in terms of is it trying to find out how life formed on Earth, or is it finding out how, because we learned that the actual kind of chemical makeup of a protoplanetary disk, for example, affects the geology of a planet and things like that, and it's like really important. So what the kind of main in the community? What's the big push? What's the scientific push in over the next, say, decade or 2 decades?
You've got a huge grant. What do you do?
What?
Too many things. So there's I think that the overarching big question that in fact I think all of us that work in many different facets of astronomy is where did life come from, and are we the only planet on which life is able to have started and thrived? And what feeds that question are many different facets, of which astrochemistry is one of them. And I think as an astrochemist, I want to know how are the we kind of have an idea. We have some idea or a theory of how at least the ingredients that the Earth needed to start life arrived on the planet. We know that we needed water. We know that we needed organic material because the Earth formed really in a horrible way through massive collisions. That was really molten. You would not have wanted to be there.
Traumatizing.
Stuff must have happened only when it cooled down and it had a solid surface. And again, this feeds into this idea of late delivery of surface material, the surface material that you need. Where does that surface material come from? The outer regions of the protoplanetary disk, right? And is locked up in asteroids and comets. Where do asteroids and comets come from? The material that was present in the disk around the young star at the time that the planets were forming. Where did the disk come from? Well, it formed from remnant material left over from the collapse of a molecular cloud. So you have this thread which goes from what happened on the Earth, the material in the disk, the initial composition of the disk, all the way back to the molecular cloud. And what I'm really interested in is, how far back does that kind of inheritance go? Does it all actually start in interstellar clouds? Trying to figure out how complex molecules can get in those environments, with the idea that some of that is preserved all the way through that process. That's really exciting, because if we make these big molecules everywhere, that means that the basic ingredients are everywhere, and life, provided that the planetary conditions are suitable, should at least be able to get some kind of a start, provided there's a big if provided that. And I think that's really interesting. Just from that fundamental perspective. And we're doing a lot, as I said, through some of the examples that I give. We are really trying to determine whether or not material in the disks that are actively forming planets now, whether that material has been very processed, or if it actually does inherit or preserve some of that kind of complexity that we see in interstellar clouds.
Yeah, I mean,
Yeah.
I was reading one of your last papers. Well, trying my best to read one, and that seemed to have evidence that you'd kind of got from one of these, big molecular clouds that there was methanol in the disk. So there was some evidence that you had that it had made it as far as that.
Yeah.
And
that was quite an interesting paper. So it was a Nature Astronomy paper led by Alice Booth, who's now, she was a PhD student with me in Leeds and is now a postdoc in Leiden Observatory. And we weren't looking for methanol. We just put it in the spectral setup because we thought that might
only
be
in the
interesting.
evening.
I wouldn't be drinking methanol if I were you.
Oh, jeez.
That can go really wrong.
You're straight from the cloud.
Yeah.
Not even the tramps drink methanol.
It's a very bad idea. But yeah, so we weren't looking for it, but we found it by accident because we do these little serendipitous, let's see if that's there when we're kind of, we're looking for something else. We did find the other thing as well, but this was almost a supplementary science thing. And the fact that we found methanol there was a pretty good indicator that for that object, that disk, that the ice that was present in that disk could not have been exposed or been processed to any high temperatures, because you only make methanol ice at 10 Kelvin. You cannot make it at higher temperatures, less than 20 Kelvin. So that's why that result made it into Nature Astronomy, because it was kind of a really key. It was the second time we'd ever found methanol in a disk. We'd found it for the first time in a disk around quite a warm star. So the disk itself is very warm. And the fact that we see it at all means that, the ice that has made it into that disk must not have seen temperatures that high. So really, because
you were finding it in the ice state, or
we find it in the gas phase, but we find it in the inner region where it sublimates.
Right.
But the reason that we know it's ice sublimating is that you cannot make methanol very efficiently in the gas phase. That's something that, again, laboratory astrochemistry has determined quite a few years ago. So it's really, really hard to make in the gas phase. It's very easy to make in the ice phase, so long as you have temperatures below about 20 Kelvin.
Yeah.
So we're certainly, but again, this is one object. About a particular object, we kind of need to start to think about, is that particular to that object? Is this something that's actually more widely seen? In fact, there's two objects now. There was IRS 48 as well, where they saw actually methanol as well, which is a very weird object. It's got a big lopsided dust disk as well. So I'm gonna go ahead.
Go on. No, go ahead.
Oh, I can't remember what I was going to say. So
I was going to say, you know what I'm going to say now, right? I'm going to say my catchphrase, something I say in pretty much every single episode. We want more telescope time. This is always the answer to anything. We want more objects, more time, more science.
I think so. And but a lot of what we're doing is with ALMA. And ALMA is going to have decades-long lifetime. We're not constrained by the fact it's floating in space and might run out of coolant. It's sitting on the ground.
We can upgrade it and repair it if it needed.
Exactly. And they're looking at adding on more receivers to increase the frequency range and everything. So we have a really brilliant instrument at our disposal on the ground. It's going to be operating for decades. We will get it done. It will just take time, I think.
Well, this is something as a sort of closing statement, but something I think is so cool about chemistry is that maybe people don't realize that chemistry is a much more flexible process, let's say, than, creating elements is hard to do. That's when you're changing the proton number in an atom. Mm-hmm. But chemistry is more to do with what you do in the electrons around the atoms, and chemistry can happen backwards and forwards, upside down, and all these different things. And so it's something that could, like when we were talking about the material and the disks and stuff, I'm sure there is research about, how you can gain or lose different types of actually the types of atoms and the types of species in a disk. But what kind of chemistry is going on in a disk, that is much more something that can vary over time. And that's what I think is so cool about it.
Yeah, I mean, it's again just taking ourselves outside of the pressure and temperature regime of the Earth. You just the parameter space is huge.
It's I mean, it seems so counterintuitive. Yeah. I mean, like I mean, I've definitely learned like just the fact that you can make these complex like chemicals at very low temperatures. That just seems to me like completely
like, are you sure?
You always think you need energy. But actually, and again, this is counterintuitive because people don't think about chemical reactions in this way. But, you know, a lot of these surface reactions that I was talking about, making a covalent bond, making a molecular bond is actually usually exoergic. It's usually releasing energy. And actually what creates the molecule is the ability for that molecule to lose that energy. Otherwise, the atoms split themselves apart. So what the surface does is absorbs that extra energy and allows the bond to stabilize. So it's not that you need to put energy in, it's actually that you need to absorb the energy. Which again is very counterintuitive because you're at 10 Kelvin, right?
I mean, think about like if you have heat and something's vibrating, I feel actually when you really think about it, it's more intuitive for it to work at cold temperatures because then things are not so shaky.
And you know, there's a lot of people that work on, you know, combustion chemistry, for example, which tends to be quite high temperatures because they want things to burn. That's a very neat, you know, that happens under very specific conditions. That you get that kind of chemistry happening, but you don't always need an input of energy to create a molecule. And in fact, you can do a lot without any energy at all, or very little energy. You still need things to meet. You still need things to collide, even on a surface. So long as you have enough energy and enough time for things to meet, then you can do chemistry in space.
Yeah. I mean, astrochemistry seems to sit somewhere between astrophysics and astrobiology, right?
Yeah.
It's got the astrophysics, turns into astrochemistry, that eventually turns into astrobiology. But I feel sorry for the astrobiologists because presumably they've got a sample pool of nothing so far.
Give them 20 years. Give them 50 years.
I think, you know, astrobiology is really changing as a field, I think, from... I think people would have said... you know, even maybe just 10, 15, 20 years ago, that it was incredibly speculative, that it was a lot of hypothesizing without experiment, but it's definitely gone the other way now. It's definitely a lot more about experimentation, a lot more about field work and figuring out how life survives in extreme environments on the Earth, because we do see life in extreme environments on the Earth, and like simulating, you know, it has moved on as a field from being quite speculative to actually being really robust experimental field, which involves a lot of field work and a lot of testing of those hypotheses. You know, under what conditions can life exist? So
there was me trying to cajole you into saying how much better astrochemistry was than astrobiology, and you defended your astrobiology.
I think it's really fascinating when I see there's so many people that are working so hard to kind of, you know, and they're really we're going in that direction. We're about here, although you can't see my hands probably in the podcast. Astrobiology is coming from the other direction and trying to trace backwards.
Yes,
and we're
meeting in the middle.
We're really still very far apart, I think, but I think that we're definitely getting there, and we're making.
It's the Eurostar tunnel. They're digging towards each other.
Exactly.
And I mean, it's something that, I mean, this would not be a real episode of this podcast if I did not mention how great exoplanets are, and I mean the fact that we are now trying to. Actually, not just detect exoplanet atmospheres, but actually characterize them and say something about what's going on this planet as a sort of climate. I think all of these things are all going to contribute to figuring out how astrobiology or exobiology would work in principle.
I think if you give me a big load of money and, you know, say go and do what you want,
like 10 PhD students.
Yeah. Well, the big load of money I would need because I would need to build something. I think I would love a probe to go out to Enceladus or Europa. I think those are the next best places in the solar system where we might see some evidence of either current or extinct life potentially.
Well, that's why I'm excited about juice. That's going to
Yes.
Europe, I think.
Yeah.
Yeah.
So, and I think that's what we need to do. We need to start thinking about, we have a very Earth-centric view. We know what life basically needs. We know we need liquid water. It's a universal solvent. It allows molecules to self-assemble, which is really important for building structures that then life kind of builds itself upon. We need to go to where we know there's liquid water, and we need to look there. And I really hope that a sample return mission or a probe that would go through the plumes that we see out that way. I would really hope that something like that.
Theme park ride.
Yeah, that happens in my lifetime, because I think that would be
But I mean, that just shows how far that field has moved. I mean, just the fact that we called it the Goldilocks zone, and yet really the two best candidates sit outside of the Goldilocks zone, right? And Enceladus and Europa.
They have the right conditions. It's just not surface conditions, and that's something that we have to think about again from the Earth.
Let's not be surface biased.
Yeah, we have surface bias. Yeah.
Well, I mean, you might even be chemically biased. Like go to Titan, and you might find that there's even more fascinating kind of biological chemistry going on.
Well, there is a mission to Titan that will be the Dragonfly mission. So that's already going to happen. So, and it will be a little helicopter that will fly around.
That's insane.
Which is great.
I love space.
So I think Titan's got a tick.
Tick for Titan.
And
that's the hashtag.
I think the icy moons, I think, is something that we should think about, definitely.
Yeah.
Yeah, someone was trying to explain the problem with the icy moons and the fact that the ice is so thick.
It is really thick.
We've never driven anywhere near that far, even on Earth. We were not even the Russians with all their gear.
I think we've only got a few kilometers, haven't we? Is it like maybe 10 kilometers rings a bell? But
it's embarrassing, really.
You might.
It's not even scratching the surface, is it?
But this is where the cracks and the plumes, where the water can actually things can escape to space would be the thing to do.
It'd be it's undoubtedly the most exciting mission ever, wouldn't it?
I think
either of those two things. I mean, that Dragonfly mission.
So if I had that 44 billion, that's what I would do with 44 billion.
What instead of buying Twitter?
Exactly.
That's a point. That's a really good point. What the hell's Musk doing? I'd rather have
what you could do.
He's even got the launcher.
Don't even need that.
He can even do it cheap.
I think it gives you a sense of the priorities of
maybe.
Yes.
I think so, unfortunately. Wow, this has been so cool and so great.
Well, it's been really good. We've had 3 guests in a row, which have all these kind of on a sort of common theme.
Astrobiology, astrogeology, astrochemistry.
Oh, great. Brilliant.
And this is tied it together nicer, actually, because this talking about astrochemistry actually is a great bridge between sort of astrogeology and astrobiology, because a lot of it is, the conclusion for a lot of them is it depends on chemistry.
it really did. Like that whole idea of a planet maintaining its atmosphere and having plate tectonics was all about, what was the chemistry of the disk before it collapsed. It was amazing.
It's really important. And I think we do probably need to talk more to each other, which we are trying to do. It's just really hard at the moment with no conference. Well, conferences are starting to come back again. But, I do miss those conversations that you would have with somebody who, gave an astrobiology talk and like, I'm really interested to talk to you about something you said. And this is how you make connections between the fields and things as well. Yeah. So we do need to have definitely more of those cross interdisciplinary discussions.
Because the space industry is both very good at it compared to maybe some other fields, but also definitely needs more interdisciplinary collaboration, let's say, because a lot of people specialize into something, and then and
I think part of it is that we do our PhD, we start working in a particular area, and we're safe there. We're safe in our area, and when I go to talk to other people, they know more about that than I do, and we really need to kind of just get rid of all of that
Yeah, everyone wants to be the king, having the king of their domain kind of thing, and be expert in their field. But it'd be great too. Yeah,
a little bit. But I think funding bodies, funding councils are definitely moving more towards trying to award funding to interdisciplinary research, and certainly in the UK, that's now a given. I think it's really hard now to get any grant without saying that you're transformative in some way and transcending.
Saying that you can do exoplanet stuff.
Yeah, well, exoplanet helps. But being an astrochemist, I work with lots of different people. So I'm really lucky in that I already have that interdisciplinarity built in. And I think it really helps because, I can just go to chemists and ask them quite naive questions and they're happy to do that. The same the other way around. So just kind of being in that already in a field that does bring together a lot of diverse people really helps break down those barriers between the different fields. And I think that we definitely need more of the planet formation, planetary evolution, protoplanetary disk, astrobiology people all getting together and talking more, definitely,
How did you get into this field in the first place? What was your journey to becoming
completely by accident. I did not plan it.
Slipped on a banana peel.
So I did a degree in applied maths and physics. That was my primary degree. And I was choosing my final year project. And I saw a project that looked really interesting. And it was in the Atomistic Simulation Centre at Queen's University, where I did my undergraduate. And it was about building a quantum mechanical model of water. So I actually did my master's level project in what they call atomistic simulation, or you could call it molecular physics, right? Or quantum chemistry, right? It's all the same
Depending
thing.
how fancy you want to sound.
Depending who you talk to. And I really enjoyed that. And actually, the work that I did didn't make it into a paper, but it certainly inspired a paper that was done by another researcher in a couple of years, which was really nice to see as well. So they were excited enough by what I'd found that they'd actually written up a PhD project to keep working on it. But
cool. Oh no!
And my PhD supervisor just recently joined Queen's. That's Professor Tom Miller, who came over from Manchester. And he's an astrochemist. He's one of the kind of big astrochemists that's been working
the OG
for many decades, especially in kind of the compilation of reaction rate data for use in databases, and also looking at extreme chemistry in like around evolved stars and star forming regions and everything as well. And he wrote up a PhD description for looking at chemistry in protoplanetary disks, and I was like, oh, that looks interesting. So it was really just a whim. I went to talk to him. I kept being interested. I started reading up a little bit about
Thank God.
it. And I had to go, sorry, guys, I'm going to go over and do astrochemistry now. And I ended up staying there to do my PhD, but it was not by design. I did not know what astrochemistry was before I started my PhD, which sounds ridiculous now, but it just triggered enough of my interest that I was like, I'd really like to do this. Yeah.
Well, that's the cool thing about astrochemistry, because it's already kind of an interdisciplinary subject. You can come from the chemistry way or from the astronomy way. Yeah,
and kind of luckily enough, I had my astrophysics background was fine because I'd taken those modules because I just wanted to do a very flexible undergraduate degree. So. But I'd always loved maths as well, so I liked having the applied maths. But Queen's is has a big centre of kind of just molecular physics as well. So I got really good background in that too. And I think that I could see that what I had been doing could be applied to the PhD project. So completely by accident, not by design, a bit on a whim, but it all worked out in the end, which is great.
It sounds like it.
It's a really good story, isn't it? That you can go, that you just do the things that really interest you and you kind of find a place.
That's kind of what I did. And I kind of do advise students to do that now. I think it's don't overthink it too much. Are you interested in this? No, don't do it. You don't want to wait. Or kind of, no. Follow what you're interested in, and then you'll commit yourself to it. you'll stick with it, because doing a PhD is really hard.
Yeah.
And it's a huge amount of, emotional effort, as well as just, putting the time in to get all the work done. Do something that you're really interested in.
Absolutely.
Follow your whims, follow your heart, follow, just something piques your interest, and then go and explore it, I think. Yeah.
And I mean, scientists are unhinged anyway. We're psychotic because we are so obsessive. Like, nobody should dedicate their whole life to one little thing, but we do it and we love it. And I'm so glad we do it. So, I mean, you already have to have a sort of a level of...
a little bit of a... Yeah. There has to be a little bit of an obsessive...
Yes, for sure.
Nature there. But it never should be to the extent that you don't take your holidays or your weekends off.
No, absolutely not.
You still have to, and I think that we are getting better.
Yeah.
With the team that I have now, I'm like, work-life balance. I don't work weekends.
Yes.
You shouldn't work weekends.
Absolutely.
But if you want to, that's fine, but you shouldn't.
Yeah, exactly.
Because they get worried, because they go, but I really need to get this thing done. That's fine, but take Monday off then, right?
Yes, exactly.
Yeah. So, I really try to kind of instill that, take your holidays.
Yeah.
Stop working in the evenings, with some flexibility, because everybody's different. If you're not a 9 to 5 person, you don't have to do 9 to 5. You can do 10 to 6, or you can do 8 to 12 and take 2 hours off.
Yeah.
And, so arrange your working week how you want, what works for you, but don't overwork. Yeah. Don't do more than your 40 hours a week, because that's all it takes to do a PhD. You don't need to be doing 60, 70 hours a week. So long as you're well organized, you're on top of things, you ask for help when you need it, you can get it done in 3 years, 4 years.
It's really nice to hear you say that as well, because I think that's a lot of PhD students have that anxiety as well, where you feel like you have to... I mean, at the end of the day, it is, quote, just a job, in the sense that it doesn't have to be your entire life and personality and your legacy and whatever. Like, you can be passionate about it, and it's great to be passionate about your job, but that is what it is at the end of the day.
It is, and I think that, you end up with sometimes this burnout because you devote so much time to it, and you basically end up sick of it. Whereas if then you really need to
pace
take a
yourself.
Pace yourself, exactly, and make sure that you keep, hobbies on the side, and that you take time to do other things. I used to always, I would never sacrifice my weekends, because my brain just needs a break.
Same.
Friday, I switch off. Monday morning, I come back, what was I doing? Right. Oh, that's why that wasn't working.
Now you have the clarity.
It's almost as if society has realised you need a weekend.
Yes.
Right?
And more, 3 days, really.
If I could go to a 4-day working week, I would, because I think that extra day would bring even more clarity on a Monday.
I think so. Yeah.
I think the extra 5 days.
I think I have a problem. I probably have a problem where I may be too nice to myself, because I very much try to do this thing, because my philosophy is that I'm, some people say things like I'm not here for a long time, I'm here for a good time. But my philosophy is I am here for a long time, and in order for me to stay around for a long time, I need to be having a good time.
Yeah, well, that's a good
and
point.
So I very much try to
party.
Yeah, exactly. Well, respect my working hours, and sometimes I'm like, am I being too relaxed? And then I try to convince myself that no, it's okay.
No, it's okay, and you should never punish yourself for taking time off and doing something else. I mean, that's the worst thing you can do. If you need the time off, take the time off, because you will feel better for it after you've decided to do that. Yeah.
Career advice as well on this podcast. We got everything.
Podcast advice from Catherine on work-life balance.
Oh, I like that. I'd tune in every week.
Thank you so much, Catherine, for joining us.
Thank you
been
for the opportunity. It was very nice to kind of just sit and chat about science and
reflect about how awesome your job is. Yeah,
I know, it's kind of like these kinds of chats that are kind of increase the enthusiasm a little bit after you've spent all day doing very boring things and writing emails, trying to find out information, and you can't figure out who to talk to. It seems to be mainly what I do every day, is trying to figure out who it is I need to talk to find something out.
I mean, I often think this that sometimes, like when you're like PhD science type stuff, where it's a lot of number crunching and there's lots of kind of you're really in the woods, aren't you? And I guess it must be nice occasionally to sort of go, oh, that's what my work.
Yeah. This is amazing. Yeah. There's no answer sheet. This is the harder thing. Like, there's not like you don't do your assignment and publish a paper and then you check some magical book and you're like, am I right? Did I do it? Oh yeah, full marks. Like.
And it's like, activities like this, I think, are really useful. It's a two-way thing for me because it helps me vocalize and think about the bigger picture and why we do things, rather than just sitting and doing them and writing the paper and ticking the box and things like that.
Yeah.
Well, I really like doing public talks and podcasts, and I did one for UKRI Literature Festival. I don't know if it was listened to by anyone. So I kind of...
You will now, and now everyone's going to go listen to it.
I enjoy this process of talking through why we do what we do. So it's really useful, I think, as well for us. It's a two-way thing, so...
Yeah.
I think it's amazing. I'm sure that there will be many listeners who will not have thought of even the concept of astrochemistry before, who will now be Googling PhD in astrochemistry.
Yeah, I hope so.
Yeah, it's so great, and it's been so nice catching up with you, Catherine.
Yes, I know. I'm sure we'll see each other at some point.
Absolutely, would love to have you back sometime.
Yeah, definitely. Come and visit us and leave.
Bye-bye.
Yeah. See you later.
Bye.
The Interplanetary podcast is alive!
There you go, Lynn. I thoroughly enjoyed that chat.
I loved it.
With Catherine. She was absolutely awesome. What have you got planned for the next few weeks, other than writing the next amazing episode of the Interplanetary podcast?
I think I'm going to be brushing up on my astrochemistry. Actually, one thing that we totally should do is I realized listening back that we talk a lot about astrochemistry in kind of a cold-ish regime, but there's also astrochemistry happening in the atmospheres of stars. This is a very cool other side of astrochemistry. We should get someone who can talk about stellar atmospheres. And especially, when you're looking at star-like or solar-like stars, then there's less chemistry going on because it's really quite hot that molecules and stuff like that can't survive. But cooler stars, like more like red dwarf stars or M dwarfs and stars like that, they can have things like titanium oxide in the atmospheres of the star.
Oh wow!
Which is very cool.
Well, there's been quite a cool picture of our own sun, hasn't there, by the European Solar Observatory, which is like some mega pixel.
Yes, exactly.
I was like looking at it on my computer screen, going, "No way!"
Exactly.
It's crazy.
It's crazy. I also read apparently. I wish that we still had Catherine here to confirm this. Apparently, one of the things that we have found in space is urea. The thing that you find in urine. Just incredibly off-putting in my mind to have a big urine cloud floating around somewhere.
Well, yeah, this is a thing about nebulas, though, that they're very nebulous.
Yes, exactly. It's a fine mist of urine, more like.
I would, and when we say fine mist, we're talking fine mist,
like really fine,
unbelievably fine mist.
Yes, exactly.
Yeah, you're like bumping into a molecule is going to be lucky.
Yeah, exactly.
When you're
can
there.
be like,
but anyway.
Yeah, I'm still probably not going to go.
No. I'm not going to go to any form of nebula anytime soon.
I'll stay here.
I'm probably stuck to the Earth, unfortunately. I'm never going to escape the gravity well.
No, life's unfair.
No, that's so unfair. Right. That's it, Lynn. Shall we? Until next month.
Let's go read about urine in space. And
I'm
we'll
definitely going to read
month.
about. Yeah, absolutely. What animal? In the meantime, what animal weed in space to create that urea mist? That's what I want to know. It's a very big space worm or something. Definitely
a whale.
Yeah.
Some kind of hitchhiker's reference.
Yeah, a whalian.
Yeah.
Right. Bye.
Bye. Bye.